So now we're going to talk about polyprotic acids. So polyprotic acids, the way that you identify them is they're going to have a structure that has multiple H's listed out front, all right, that could possibly come off and dissociate into water to make hydronium. The two types of main polyprotic acids you could see are ones that have three H's. Those are a bit rare. The most common one is one that has two H's to come off, okay? And like I said, you know that this is the setup, or this is like the way that you identify a polyprotic acid, because it's not just something like a simple H out in front like HF or acetic acid. There's more than one. So what do we view in terms of the chemistry? Like, how do we view that chemistry? The multiple H's come off, but they're done at one at a time. So they come off one by one, right? Each time an H comes off, it has its own Ka, because most of these species are weak, and so it has its own ice table. So you're going to see Ka1s and Ka2s. The number here refers to the H that's coming off. When you do a Ka1 calculation, okay, and you use the first ice table, that info then gets passed to the second ice table that utilizes Ka2. If you have three H's that are going to come off, you repeat that process and you keep passing information down to the until you get to a situation where you're done with K's, until you run out of K's, until you run out of H's to give. There's one exception that we mentioned before, and that's H2SO4. H2SO4 is definitely a polyprotic acid. It says that there are two H's that could possibly come off, all right? Most of the time, our H's are going to come off with a Ka and an ice table, but we know that the first H in H2SO4 is strong. So if it's strong, how does the first H come off? The first H comes off with a full dissociation, and then the second H will involve an ice table, right? So it's a little bit confusing until we apply it to, all right, an example. And you can see the mechanics behind it. Again, we're still dealing with acids and bases, so the 5% rule applies a lot of the time, and the stoichiometry means that the actual mathematics isn't too bad, okay? It's just about, again, identifying the correct chemistry. All right, so here's an example. What's the pH of a 1.00 molar 1.00 molar H2S solution? Also calculate the concentration of S minus 2 at equilibrium. Okay, so here's a problem that we're going to be able to do after our discussions in this video. All right, so we always do this identification step, right? And we identify what we're being asked. So here's H2S. We ask ourselves, is it an acid? Is it a base? Right? Or is it a salt? In this instance, I see it's something that starts with an H and it's aqueous. This is definitely an acid. I like to kind of write that at the top. I don't do like my salt techniques now. I know it's an acid. So I'm looking for Kas. For this species, it has two different Kas. It has listed a Ka1. That's 1.0 times 10 to the minus 7th. And it has a Ka2 listed, all right? That's 1.3 times 10 to the minus 13th. So we see that it has two H's, and so not surprisingly, there are two different Kas, all right? Just to make this clear before we get into the math, if I asked you to show H2S acting like an acid based off of what we know, do you know how to do that? You know you will react it with water. It's an acid. So one of the products is H3O plus. And then you can look at this structure and you could draw the conjugate base, right? This is the first H coming off, right? This was when it lost its first H. So whenever I do math associated with this, right, I'm going to use Ka1, again, because the first H came off. But after that first H came off, we see that there's still an H that remains. This guy could be an acid or a base, and we'll talk about that in a bit, but we already decided at the top that our solution was acidic. And so this guy doesn't have a choice. We know it's an acid, so HS minus can react with water, just like any acid we've ever written, any acid reaction, and we can make H3O plus and the conjugate S minus 2. Now, which H came off for this second? So everybody see how it's one at a time. You just keep writing the same chemistry we've been writing. Take the first H off. There's still an acid present. There's still an H that could be given. So because it's an acidic solution, we do it again, right? This is the second H that came off our main species, right? So this would utilize a Ka2, okay? So this is essentially what our mathematical setup is going to sort of look like, or a chemical setup that we're going to base our mathematics on. Going to do an ice table with this weak species, and I'm going to figure out, all right, what the first dissociation looks like. I'm then going to do a second ice table, taking information from the first to make it, okay? And then I'm going to build a second ice table to finish off the problem, all right? I'm going to stress this as we go through the math, but notice, right? Where's the HS minus coming from for our second ice table? It's coming from our first ice table, right? Where's H3O plus coming from? Do we say any H3O plus is there to start with? No. Where's it coming from for our second ice table? It's coming from the first ice table. Information from our first ice table is going to be translated down into our second ice table, okay? Again, hopefully it becomes clear as we go through this problem. So now we have it mentally set up. Let's try this. All right, we have a 1 molar solution of H2S. We know it's a polyprotic acid. We have our Ks. Let's start one by one. H2S, H2O, H3O plus, HS minus, ICE. It's a weak species. All right, water goes away. We were given an initial concentration of H2S. That's 1.00 molar. Our initial concentration of H3O plus is 0. HS minus is 0. Q versus K. Q equals 0. Q is less than K. All right, definitely moving towards the product side, moving towards our zeros. So we're going to put some minus X, put a minus X here. Plus X on the product side, X, X. 1.00 minus X. Within build our K expression, we remind ourselves, this is the first H coming off. This chemistry is the first H coming off of that structure. So I'm going to use Ka1. Ka1 was given as 1.0 times 10 to the minus 7th. Okay. This is going to be equal to X squared divided by 1.00 minus X. Again, we have a candidate for the 5% rule, and we can do our check, all right? You're going to check my work, but when I do this math, right, when I solve this for X, what I get for my X is I get, let me check my notes, 3.16227 times 10 to the minus 4. I get 3.16227 times 10 to the minus 4. Let me just check that quick. Okay, good. All right. I'm going to keep track of significant figures. All right. I have 2 significant figures here. So now if this was the end of the problem, we could get a pH from this number and we could analyze it, but it's not the end. As we said last time, on the last sort of thing before I erased it, it's not just a Ka1 we have to worry about. We make this guy, right? And in fact, we know how much we made. We made 3.16227 times 10 to the minus 4th molar. Because how much we make in that first ice table, that's our X. And in fact, we also made some acid. That'll contribute to the pH, right? How much do we make? That same amount in molarity. So we're not done yet. What we're going to do is we're going to write a second ice table. Now, you've written this down in your notes, right? Just for the sake of showing where this information is coming from, right? I'm going to draw the next ice table right below this. We're not done. Another H could come off. H2O, H3O plus, S minus 2. Okay. I, C, E. I, C, E. So now I look for my I information. Well, again, how much H2S minus did you have at the very beginning? None. But what did you just do? You figured out that after the first H comes off, you made your previous X. You made that much. So that information right here becomes your I information for your second ice table, right? Information from the E comes down to the I for your second ice table. So this is going to be 3.16227. So I'm going to write it 3.162 times 10 to the minus 4. Right, molar. I'm going to cross out my H2O. Right. How much H3O plus did we make? Again, E information translates down to I on the next table. 3.1622 times 10 to the minus 4. And you're going to have more space, so you don't have to truncate it as much as I have. All right. How much S minus 2 do we have in our first ice table? None. How much S minus 2 was there to start? None. That's a 0. We do a Q versus K again. Q equals 0. Q is less than K. We move to the right side. This is going to be a minus X here, a plus X here, and a plus X here. All right. So this E right here is 3.162 times 10 to the minus 4th minus X. This E right here is 3.1622 times 10 to the minus 4 plus X. And this right here is our X. Okay. So one more time just to review. We use our first ice table to set up our second ice table. Where are these numbers coming from if they weren't given in the beginning? They weren't given in the beginning, but we made them with our first ice table. Okay. We have a setup. We have a K because this reaction describes the second H coming off of our parent structure. All right. Notice the blue X and the red X, the blue X and the black X are going to be different. The X that we used up here became a number, but now we have another unknown down here that we can solve for. And how are we going to solve for that unknown? We're going to use KA2. We're going to use KA2 because the second X is coming off. The second H plus is coming off. We're going to solve for our second X. So KA2 was given as 1.3 times 10 to the minus 13. Really small, really weak dissociation, right? This is going to be equal to 3.1622 times 10 to the minus 4 plus X. That's my H3O plus concentration. My S minus 2 concentration is X. Okay. My HS minus concentration from my ice table is 3.1622 times 10 to the minus 4 minus X. Right. This is actually a really nice example. It's an easier example because this is so small, we can use the 5% rule again. Oftentimes for this second ice table, it doesn't always work out that you can use the 5% rule again, but for this one, it'll work. And notice what happens when you use the 5% rule and why this becomes so easy. Just look at the magnitude difference here, and we're moving in the unfavored direction. Definitely 5% rule. If I use the 5% rule and I get rid of this and I get rid of this, right? These numbers just cancel out. And what you get is a real interesting result. For this situation, which again is an easier example, you get that x is 1.3 times 10 to the minus 13. Now we're going to answer the question, right? We want to know what the pH is. What you're going to be tempted to do, because you're so used to dealing with monoprotic acids that just give one H plus, you're going to be so tempted to do the negative log of x. And what you're going to get is a nonsense answer that's not going to work, right? So for polyprotic acids, remember, right? What you need for pH, not only for polyprotic acids, but what you need all the time is you need, right, the negative log of your H3O plus concentration at equilibrium. Is X my H3O plus concentration at equilibrium for this example? No, because if I look here, here is my last H3O plus. You find the last E spot under H3O plus to do this calculation. This is when it's done. Both H's have come off, the chemistry's over. This right here is the accumulated amount of H3O plus that both dissociations made, right? What this X is in terms of answering a question, even though it's not our H3O plus equilibrium, our X is our S minus 2 concentration at equilibrium. So because we're going to go on and do some work down here, I'm just going to make that note. Right here, when we do get this X, if I look down at the E underneath the S minus 2, the concentration of S minus 2 at equilibrium is equal to 1.3 times 10 to the minus 13 molar. That is an answer that we can use. pH, though, is going to be 3.162 times 10 to the minus 4 plus this very small number. Take that value to the negative log, and that's going to be your pH. So make sure you can confirm this number mathematically. But what we end up for pH, because we're going to use the correct value, your last H3O plus in your last ice table, the equilibrium value, right? What I get for the pH when I do this, and most of the H plus came off in the first dissociation, and that happens a lot. What I get for the pH is 3.50. Remember way back at the beginning we decided it was an acid. Is this an acidic pH? Yeah, it is. Okay. So it's again mathematical skills that you have and that you can utilize, but it's just you might have to do multiple ice tables if there's multiple Kas. All right. So it gets a little bit complicated when we start to discuss. Sorry, I hit my camera. I'm just going to check and see if everything lines up. It gets a little bit more complicated when we start to discuss salts containing amphiprotic anions. All right, salts containing amphiprotic anions. To continue with like this last example that we went over, all right, what happens if you see and you're asked to analyze something that looks like this, right? And you're asked for the pH. Well, it's a metal attached to a non-metal. So from our recognition step, what do we say? We say, okay, yep, this is a salt, right? I'm going to take my salt and I'm going to break it down into a K plus and an HS minus. And remember, we haven't said whether it's acidic or basic. Remember, salts, they could be either. They could be neutral too. So we haven't decided whether it's acidic or basic. So we do our normal dissociation. Hopefully by now, you know, we get rid of the K plus because it comes from KOH. It's not going to have any effect on the acidity or basicity. We got rid of K pluses even last semester as spectator ions all the time. And it's the same thing here. They're just kind of spectator, not watching what's happening. All right. Now we see HS minus. And this is a form that you have to recognize. This is an amphiprotic anion. So how do I know that this is amphiprotic or amphoteric, right? And remember, those words are synonymous. When I take a look at HS minus, what I have is something that maybe wants to get rid of an H because it starts with an H. It's going to be in an aqueous environment. So maybe it wants to get rid of its H, just like we saw for this last example. But I also see that it has a negative sign here. So it has a spot for an H plus. So that negative could attract an H plus. And if it grabs onto an H plus, it would be acting like a base. So it has an H plus that it could lose, right? Or it has a spot for an H plus where it could gain an H plus, right? It has a spot to be an acid if it loses that H, or it has a spot to be a base if it gains an H. So just like water, sometimes this will act like an acid, and sometimes this will act like a base. One of the ways we know it'll act like an acid is if it's in an acidic solution, it can just kind of keep adding to the acid content, right? For a polyprotic example, just like our last one. But what if it's a situation like this, where you've identified it's the only thing in solution that's going to be affecting the pH? How do you decide whether it's going to act like an acid or a base, right? So whenever we have this amphiprotic situation, and one more time, amphiprotic means it starts with an H. Amphiprotic really means it could be an acid or a base. The way we identify these anions is they start with an H, but they still have a minus, right? How do you decide how it's going to behave in solution? You do a Ka versus Kb check, right? That's what decides how it's going to act. So for this solution with our KHS example, what we want to know is, will the solution be basic or acidic or neutral? Now we already know it won't be neutral because we do have this thing that's either going to be acidic or basic. So now we have to decide acidic or basic. We do a Ka versus Kb check. Now please pay attention, because it's one of the things that really confuses students. But here's what we're going to do, especially as we're learning it every single time. Once we identify that we have one of these species that could be an acid or could be a base, we've already decided that we don't know at the top of our problem, so we get to check Ka versus Kb. What I recommend doing is write down the chemical reactions one more time, because we know that for H2S, there are different Kas, right? And so there's going to be different Kbs, and you have to pull the correct information into the correct spot to make sure that you're doing this correctly. So here's what I mean. I know that HS minus, which is the thing I'm really analyzing, comes from the reaction H2S, H2O, gives me H3O plus HS minus. I know with this reaction, right, H2S shows up, right, as a base. It shows up as a base. And I know from my last video that I can calculate the Kb when it's showing up as a base. And Kb is Kw over Ka. So that's not too confusing. Like, that should make sense. We did that in the last video. Yep, here's a conjugate species. I know how to calculate a Kb from a Ka. Here's what's confusing. HS minus can also act like an acid. And when it acts like an acid, we know that it has a certain Ka associated with it. Okay? Now, the Ka versus Kb check means that what we do is we look at Ka and Kb, and whichever one is bigger, that's how it behaves. So here's the thing that you need to get used to doing. Which Ka do I divide by there? Because the thing about polyprotic species is, remember, for this reaction, we have a Ka1. And for this reaction, we have a Ka2. And the easiest mistake that students can make for something like this is they divide by the wrong Ka. So how are we going to avoid that? We're going to write down the chemistry, and then ask ourselves this question. Where is HS minus, this thing we're analyzing, where does it show up as an acid? Hopefully you can look here and see this is acting like an acid. It's donating its H. This is where it's acting like an acid, so that's the Ka that I need to use in my check. It's all about HS minus. We want to know what its Ka is and what its Kb is, and whichever one is bigger tells us how it will behave. This right here, is it the first H coming off or is it the second H coming off? It's the second. So if you can identify that this has a Ka that is Ka2, what you're going to remind yourself is you never use this Ka to divide, right? The Ka that you use to divide and get a Kb comes from the equation where that species that you're trying to analyze is on the side as a base. Here's it acting like a conjugate base. Here's the side, here's the reaction where it's acting like a conjugate base. Just following the logic from the last videos that we had. This is the Ka1 equation where it shows up as a base. So I'm going to divide by Ka1. One more time, just to make sure you kind of realize. See how it shows up as an acid here? Then you're kind of done with the thought process. If you already know it's an acid, you have the Ka. If I'm trying to calculate a Kb, is it acting like a base here? No, so I'm not going to use Ka2 information to calculate Kb. I'm going to find where it's acting like a base. That's in the Ka1 reaction. That's what I'm going to use to get, all right, what Kb is equal to. So until you get completely comfortable with this, I really recommend write down both, write down which K it is to the side, find the species acting like an acid, identify its Ka that way, and then just tell yourself, if you can identify where this is acting like an acid, never, ever, ever use it, right, to calculate a Kb. Because if it's acting like an acid, you already know what its K is. Find where it's acting like a base. That's what you're going to use to calculate Kb. So then with this identified, let's finish this problem. All right. Ka2 is something that you'll just be given for a problem like this. So just like our last example, Ka2 is 1.3 times 10 to the minus 13. That's the Ka for HS minus. So that's where HS minus is an acid in the chemistry that we write down. Kb is going to be Kw over Ka1, which is 1.0 times 10 to the minus 14, divided by Ka1, which was given to us in the last example, is 1.0 times 10 to the minus 7th. This math works out to be 1.0 times 10 to the minus 7th. That's just luck, you kind of do the math. Now look, we're trying to decide whether this salt is going to produce a solution that's basic or acidic. Whichever K is bigger wins. And that tells you whether it's going to be a base or an acid. For this situation, hopefully you can see that Kb is way bigger than the Ka that we're looking at. All right? You don't even have to put the subscript there. You just kind of see the numbers. The Ka that we're looking at is 10 to the minus 13. The Kb is 10 to the minus 7. Kb is way bigger. So guess what our answer is, all right? If KB is bigger, then this solution is definitely a base. It's a basic solution. Okay? So it's about making sure you understand the chemistry again and being able to write it down and being able to identify the correct Ks to use to do manipulations that we're familiar with, but now it requires a little bit extra organization, all right, based on the idea that some species give up more than one H when they go into solution. Okay? If this was a problem and it asked for a pH, here's your KB, you know it's a base, right? This will be the last thing I write down. If this asks you to calculate the pH, what you would do is you would say, am I going to write the acid equation? No. I decided it's going to act like a base. So that HS minus that came from our dissociation is going to react with water to make OH minus and H2S. All right. Do I have a KB to use with this equilibrium? Can I set up an ice table? Yep. And you would need to be given an initial amount of this, and this will be some number, cross out H2O, and you go from there like normal. And again, it's a simple ice table. Probably going to be able to use the 5% rule depending on what this initial concentration is. All right? But then you're set and you're done. But it's all about this initial work to figure out whether you have acids or bases, right, for these amphiprotic situations. Okay? So try to digest it as much as you can. And as always, contact me for any help.